This country's often had good reason to be glad that it's an island. The English Channel kept Adolf Hitler off our doorstep, and of course the seas around us put paid to the Spanish Armada. But everything has to be paid for. England, Scotland and Wales alone has an almost unbelievable 6,000 miles of coastline, and sometimes the sea can come at it with remarkable ferocity. This film, then, is about the work of those latter-day Canutes, the engineers whose job it is to keep the sea at bay, and whose best efforts are, ironically, often invisible.
About 700 miles of coastline needs reinforcing. South of the Humber, for instance, right down to the Thames Basin, much of the south coast west of Brighton, and the coasts of North Wales, Cheshire and Lancashire up to the Ribble that enclose a specially interesting area, Liverpool Bay. Here, a lot of factors: 30-foot tides, strong winds that build up the waves across 70 miles of Irish sea, and complex currents combine to make things tricky for the maritime engineer.
This is New Brighton on the Cheshire coast, and I suppose its name gives a clue to its pretensions as a holiday resort. But if I were walking here 50 years ago, I'd be on a luxurious beach, because in those days the sand used to come pretty well up to those houses over there. So all this 200 yards with its paddling pool and its sunken tennis courts and bowling greens, not to mention the splendid sweep of the promenade, has been reclaimed from the sea by building a sea wall. And it certainly is a very considerable piece of engineering. But the sea can play some very unkind tricks. Well, they found that out at Southport, another northwest holiday resort about 20 miles up the coast. When I was taken for my holidays there about 40 years ago, I could be pretty sure of getting to the sea for a paddle. And not long before that, they actually used to anchor the coal boats and unload them at the end of Southport Pier. Well, the sea scotched all that by depositing huge volumes of sand on Southport's doorstep. Here, the sea played another dirty trick, only this time it did it in reverse. Instead of dumping the sand, it started to carry it away. And the source of New Brighton's downfall was, curiously enough, the same source as that of its newfound pride, the King's Parade sea wall.
New Brighton between the wars thrived on its golden sands, but competition was fierce. Blackpool was only one rival that offered sun and fun for all the family. Blackpool's pride and joy was a miniature Eiffel Tower, a positively Parisian exclamation mark at the end of their generous promenade. New Brighton just had sand. So, to start with, it built its own tower, taller than Blackpool's, and with at least as fancy a ballroom. But then Southport, for instance, had a ballroom too, and if that wasn't quite as flashy, there seemed to be more to offer all the year round. The Lord Street shops had a legendary elegance, and the upper crustness was reflected in the upmarket beach rides. On the whole, variety seemed to be the best bait, and a touch of class. So, the less elegant New Brighton's answer was a super prom. In 1926, the local paper published the plans. Sunken tennis courts and bowling greens sheltered from the wind, a swimming pool, a boating lake, and bags of opulent space. The contractors moved in and built a cofferdam to keep the sea out while they built the wall. The sea, hint of things to come, moved in and knocked the cofferdam over. But in the end, the wall was finished, one that could indeed, in the contractor's words, resist any tempest. It wasn't long before the smiles faded. Something was going wrong, and it looked very much as if New Brighton had gained a promenade and lost a beach. In charge of Wallace's coastal engineering these days, Philip Barber.
Well, this sea wall was built just before the Second World War, and it was built to the best technology available at the time. But unfortunately, the profile is a hydraulic disaster, is about the only way I can think of describing it. It's structurally quite magnificent, and indeed any inspection of the wall would show it to be in good shape for 40 years service. But the hydraulic disaster results from its profile, which reflects every wave that hits it. It's just like light bouncing against a mirror, and indeed waves behave very similar to light rays. The waves hit the wall, they've already travelled over the beach once, and by being reflected, they travel over the beach again. That means that by such a wall, you are doubling the energy expended upon your beach, and quite naturally, that tends towards erosion.
With a brisk breeze and a high tide, it's easy to see that happening. The waves are blown in across the bay from the left, but there are other waves travelling in the opposite direction. They've hit the wall and they're bouncing back. Slowed down, the wave's behaviour is even easier to see. Here, a large wave coming in meets an equally big wave going out. The resulting explosion lifts the sand off the beach below. That's why the waves are brown. The sand in the waves should be protecting the sea wall. Instead, it's being swept away.
If the erosion continues, that sea wall is threatened, and indeed, if that sea wall moved, it would move as a monolithic structure, and it would be almost impossible to repair. So safeguarding the toe of that sea wall is of paramount importance to the authority.
There's no doubt the sand is going. Finding out where is a different matter because tracking sand is far from easy. To the west of the wall, a trench full of fluorescent sand has been dug into the beach, and with Liverpool University, the Wallasey engineers have come up with an ingeniously accurate system for following its movement. These canes mark the points at which samples will be taken. They're set out at carefully measured 50-metre intervals so as to establish a regular grid pattern. Here, the trench is on the left, the sampling points on the right. Then, at regular intervals of time, samples are taken, always the same amount of sand from each point on the grid. It's bagged and dried and taken off to the Department of Civil Engineering in Liverpool University. The sand from each of the collection points is spread out on a board. Then, under ultraviolet light, any fluorescent grains that have been washed along to a collection point show up as little diamonds of light. They're painstakingly counted.
$816.
The number of grains goes against the cross representing the collection point. The pattern that emerges from this sampling shows that the sea gradually shifts the beach sand eastwards. At last, it leaves the sampling area altogether, falls into the deep Crosby Channel, and is swept out to sea. As for the forces that move it along, well, there's an odd-looking pole about 50 yards in front of the wall that may well hold the key to the mystery of just what's happening in these sand-laden waves. For 5 years now, Wallace's engineering team has been arriving every so often at low water to arm the pole and turn it into a data collecting station. Usually, it's a Met Office warning that there's bad weather on the way that sends the team scurrying onto the beach. Sometimes, if that's when low tide is, at 3 and 4 in the morning. Like the pole, the engineers look a touch primitive in their wet weather gear. In fact, they're all highly qualified and part of one of the most advanced pieces of maritime research in the world. The project represents a long-term cooperation between Wallasey Borough Council, Liverpool University, the National Maritime Institute, the Hydraulics Research Station, and the Institute of Oceanographic Sciences. The list alone gives some idea of what a devious, many-headed monster the sea really is. The electronic circuitry will record wave heights, wave velocities, and the height of the tides.
Loaded. Take another 0.
These probes measure the force of the current flowing past them, and each identically machined perforated sphere alone costs £25.
Okay, John.
Fitted with nozzles, these intakes will measure the volume of sand in suspension at different heights above the sea bed. And all this information is fed along a concealed cable to dry land. Eventually, it becomes another mass of data in the Liverpool University's computer. At the eastern end of the King's Parade, over the 1930s Lido, a radar scanner watches the waves in the bay, and their changing patterns are automatically photographed. That, in meters, is the height of a wave 10 miles out, a figure converted into a recorded pulse on a tape and destined to be yet more grist to the computer mill. The computer is at the heart of the decisions the engineers will be making, and it's constantly comparing the theory programmed into it with the facts of the collected data. Without it, no one would be able to unravel the mysteries of waves and tides or predict the outcome of this or that strategy. With the computer, they're getting a clearer understanding of the sea's behavior worldwide. At Wallasey, it may enable them to reverse the erosion of the beach where, despite the groins, the current continues to shift the sand from the western end of the Wirral to the mouth of the Mersey. The current can carry the sand away only because the waves stir it up from the bottom as they charge across the beach. While the grains are in suspension, they can easily be floated away by the strong and complex currents. The plan, then, is to build a rubble wall about 200 yards out that will soak up their energy and leave calm water over the beach area. Then the passing currents can be persuaded to drop the sand they've brought with them. Where Philip Barber wants that to happen is at the foot of the threatened sea wall, but it will be the sea that does the work.
This is the theme of Wirral's sea defence development, to use the energy which is available, both in the tides and the waves, to either spend itself where you want it, and this is why a lot of our defences, new ones, are of shallow slopes.
In fact, Wallasey's coastline has had a sloping defensive seawall for years. This concrete was laid nearly 40 years ago as a temporary measure. But by now it's not much more than a thin skin, and it's being demolished where the sea hasn't done the job already. The drill bit goes through to nothing because the sea has got behind the pie crust surface and scooped the sand out. The answer is a different kind of structure. These concrete T-pieces are part of a new, shallower slope. Fitted together, they make a deep, egg crate-shaped framework. Each box is lined with heavy plastic sheet. On top of the sheeting, a load of gravel. Finally, concrete is poured into the box to form a slab within the frame. On the face of it, just another solid wall, but the slabs aren't bonded to the T-pieces. When the sea presses and sucks at the wall, the slabs can give a little to absorb the wave's energy instead of being smashed by it. The final result, a 3.5-mile structure that bends rather than breaks, absorbs rather than reflects, and deals with the forces of nature like the willow rather than the oak.
The wave detects the shallow slope, which tends to trip it up. It plunges, breaks, and its energy is then shed upslope until it gets tired, and then it runs back down again, so that you absorb all the energy that you have to cope with on the structure in the way that you want to absorb it, not in the way that this seawall reflects it back again onto the beach.
Parts of the coast have some natural protection, and their defences can be less elaborate. But it's only detailed research that's enabled the engineers to construct a wall quite so casual looking.
Well, it's a rip-rap sort of protection. That's its trade name, as it were. Essentially, it's using graded rock as armouring to defences, so that waves spend their energy by rushing in and out of the blocks, and the blocks are designed of sufficient weight to resist any movement by those waves.
It's not the way the Victorians would have done it, but it works and it's relatively cheap. These days, that matters.
Money really is the key to all that gets done. And that's the fun and skill of being involved in engineering.
Douglas Turner is chief engineer for Sefton Borough Council, and his patch is the 20 miles from just south of the Ribble to Crosby. It's at Southport that those unwelcome tons of sand hold the sea at arm's length, so that the seaward end of a very long pier stands for much of the time over embarrassingly dry land. Would-be paddlers have a 3-mile plod at low water over a seemingly endless landscape. The contractor's rubble road runs over a beach so flat that there's very little depth and no fast-moving waves to scour it clean. But Douglas Turner hasn't let the need for thrift put him off a grand solution.
It does fall very, very slowly indeed, doesn't it? I mean, I don't know how far it is from the actual, say, Marine Drive out to where the sea is now.
We're talking about 3 miles at low water on spring tides, and it doesn't shelve, really, it dips. And this is one of the ways in which we hope that we can, with the university, get some new project going. What we have in mind is that behind us is the horse bank, one of the great sandbanks of the estuary, and what we would like to do that is to build it up a couple of meters, closing southward onto the pier to keep all but the very highest of tides out, and hopefully we can sell the rest to finance the project.
Happily, Southport sand is very high in silica, and it's sold for use in foundries and glass making. The trucks that carry it away look like toys on the huge expanse of the beach, but they're pretty sizable themselves.
We're talking about 30 tons on each truck.
And that's a mere nothing, presumably.
Oh, they do 100 of those a day, sort of thing, and who knows where they've been. We've just been wandering out and seen the little piles. It's just nothing. So when you multiply that millions of times over, that's what we're going to be doing here. I don't imagine that we'll be moving it by trucks. The sort of concept is that we could put an ocean dredger in here with a floating pipeline that would be pumping sand out onto the horse bank, onto the crest that's there, running to form a new profiled beach seaward, and landward for that matter.
The result would be a huge offshore lake, 2 miles long by a mile wide, genuinely part of the sea, but protected from all but the highest waves. The rowers, paddlers, and yachtsmen would love it. But whether it happens comes back to that non-engineering ingredient, money.
One can see the idea of developing an offshore marina by moving the sand. But if we are talking in terms of importing major large-sized rocks from either the North Wales quarries or from the Cumbrian quarries, then we are talking again in terms of millions of pounds, and millions of pounds just aren't going to get spent. If we can use the local material, then we can maybe reduce that by 100 times.
Douglas Turner isn't talking theory. Formby Point, just a few miles south, is being saved from erosion by a combination of applied research and cheap, locally available materials. The threat to the area, though, had a lot of people very worried.
I've seen as much as 15 foot of dunes lost in one tide in that area, and the sand is being washed north and south. So what we want to look at, a lot of money is being spent in the Formby area to make better recreation facilities in the dunes.
And the dunes aren't just for recreation either. They stand between the sea and the fertile, valuable land behind them, which has no other defence against the storms that can lash Liverpool Bay.
The threat is that the dune structure is all that prevents inundation of the sea onto the Lancashire floodplain, which is a very important food-producing region.
The answer, thanks to modern research techniques, was remarkably simple, successful and cheap.
Well, here you very plainly see how simple brushwood fencing or groins placed on strategic lines very quickly trap blown sand and build up into solid dunes or groins themselves and reform the defences. And that's precisely what we're doing here, stabilising the whole area. And you can see examples all around where the frontal dune structure has got gaps in it. You can see the wattle fencing and the brushwood fencing being made up. And these were something 4'6" above the sand level. And already you can just see 6 inches of the tip of them. And they will get fatter, having grown quickly to the full height. They'll now get fatter and fatter and fatter, trap the sand and make the dune system secure.
Like Philip Barber's riprap sea wall, the fencing is anything but monumental. But today's engineers seem to be informed more by modesty than machismo.
But here, this is a different field of engineering, but it's engineering nonetheless. And a good deal of the good work that will be done rarely will be seen and appreciated by people, but it's there.
Not only is it there, it will have to stay there. Liverpool Bay is notoriously aggressive, and even these minor waves take a lot of stopping. But economic pressures mean defences to stand up to the heaviest sea for the least cost for the longest time.
The cost of sea defences has gone up very much in recent years, and it now becomes a significant burden, especially if looked at on a national scale with the lengths of defended coastline that we have. We're talking on sea walls of unit costs between £2,000 and £3,000 per metre. And when you consider that there are some 690 miles of coastline in the UK which have defences which need maintaining, such costs are clearly going to impose a tremendous burden if they have to be maintained on the national budget.
A smaller purse has meant that the engineers have had to replace indulgence with ingenuity. It's called for all the help that modern technology can give. But the biggest change has come from a better understanding of an unremitting enemy and the realization that you can't beat the sea, you can only persuade it to join you.
Well, I love the motto of the civil engineers. I think it's an inspiring sort of thing, to harness the forces of nature in the service of men.